Je suis Kulbir, je suis professeur de sciences des computational aux matériaux à l'INRS, Institutional National de la Recherche Scientifique. Aujourd'hui, je présente sur l'intelligence artificielle et changement climatique. Mon français est pas bien. Comme vous l'avez peut-être deviné. Donc, aujourd'hui, je présente cette présentation en anglais. Okay, so climate change. Right now, we all worry about climate change, whether it is scientists, economists, policymakers. We all talk about climate change. We all worry about climate change. Well, what is climate change? So it is simply an Earth's energy imbalance. The amount of energy that is coming to Earth and the amount of energy that is being dissipated, that imbalance is letting the temperature rise by 1 watt per meter square right now. And that is heating up the Earth, and that is heating up the temperature, rising. Sea levels are rising. We see melting of ice, extermination of various species, and so on. Now, if we think about climate change, when did it all start? In 1850s, British physicist John Tyndall, he's the first one to identify greenhouse gases effect. And it took us almost a century. In 1981, a climatologist, James Hansen, is the one who pointed out that these greenhouse gases are actually doing the climate change. They are responsible for the 0.4 degree Celsius rise in temperature in the prior century, and he also predicted that these gases are going to increase the temperature of Earth in the coming century. He predicted that we will see rise in sea levels, we will see extermination of species because of these greenhouse gas effect or greenhouse gases. And this work came out in Science. It was published on in New York Times in 1981. So what are we doing since then? Since then, we have been trying to mitigate the climate change. There are several new technologies that are clean and green, such as solar cells, biofuels, windmills, batteries, fuel cell cars, and so on. So it's 2022, and we have these technologies. And if you think about these technologies, advanced energy materials lie at their center. Whether we want to convert carbon dioxide into useful fuels or chemicals, or we want to have photovoltaics, or it is healthcare, whatever technology we think about, this advanced energy materials lie at the center. We need better materials, we need affordable materials, we need clean materials to produce clean energy technologies. Now I'm going to go how these materials are discovered. I'm going to go a little bit back. If we think about how these discoveries or these new technologies come into life, let's talk about a small molecule, hydrogen. It is a very powerful molecule, although it's a very small molecule. The way it interacts in any process decides the fate of that process. Now, if you think about in 1823, we were hydrogen, because of the hydrogen, how it passes through the platinum catalyst, we were able to first time commercialize the heterogeneous catalysis application in the form of a lamp. And then in 1897, Sabatier reaction, very important reaction. Here, when carbon dioxide interacts with hydrogen in a certain way, we could form methane. Then we go to 1901, hydrogenation of double bonds in fats and oils. We could make liquid oils into solids due to this. And now this market is about 52 billion. It's going to be in 2028. Another very important reaction where hydrogen was involved and that led to the revolution in agriculture industry is Haber-Bosch process. In Haber-Bosch process, nitrogen from natural gas interacts with hydrogen to produce ammonia, and that could be used in fertilizers. And that revolutionized the agriculture industry. Right now, by 2028, this market, ammonia market, is going to be $110 billion market. now I go to 1925 Fischer-Tropsch, where carbon monoxide interacts with hydrogen, and it produces liquid hydrocarbons. And that market, by 2020, was 7.9 billion. So if we just think about a very small part of the whole chemistry or material science world, which is hydrogen, where hydrogen is participating in these processes, we could see how impactful that was. So how these things were discovered throughout all these years. There were so many hidden trials that were done in an experimental labs, and so many principles of physics and chemistry were applied to identify these to have these reactions synthetically happen. Ammonia exists in nature by default, but we were able to make it in the lab by various hidden trials, right? Now, it's not just that, okay? It's always not hidden trials. It's not always like that. Sometimes discoveries happen by accidents. For example, dynamites, X-rays, radioactivity, insulin, penicillin, LSD, superglue, pacemakers, and even Big Bang. This was all happened in experimental labs by accidents. So in this world, when this is happening, there are new set of tools that came out in a couple of decades ago, computational material science tools. Why do we need them? What are these tools? So based on quantum chemistry, quantum physics, we were able to develop these softwares, these algorithms, by which we could analyze materials in computers instead of going in a lab. And we needed these tools to expedite the material discoveries. So right now, we have tools based on classical mechanics, quantum mechanics. There are several scale bridging techniques. We can make the material in a computer while sitting on a desk. We don't have to go in a lab and analyze it and discover a new thing. Now, why do we need that? To accelerate our discoveries, right? So what we do right now using these tools, this is what my lab does. We design these materials. We can design anything that you want to design in a computer based on principles of physics and chemistry. And we can also analyze those materials under different conditions. For example, in presence of sunlight, how this material would behave. And we can understand the mechanisms behind them. We can analyze those materials in presence of temperatures, pressures, and so on. Then ultimately, we use these tools to design materials. We propose new materials, and we go to experimentalists and say, hey, would you try this? And we validate these materials using experiments, and overall, we are able to contribute to carbon neutral society by accelerating using these tools. All right, so far we are not talking about AI or machine learning. Now, right now, the state of the art is we do work, when we want to discover a new material, a new process, we do experiments as well as computation, hand in hand. They go hand in hand. And now, why do we need both? We need both because if you think about experimental studies, we make a sample, we see a chemical process. It's like an elephant. We see different parts of the process. And sometimes we end up judging it in a totally different way. We sometimes are not able to see the big picture of the process, chemical process, or the materials that are made in the lab. On the other hand, computational studies, you can actually sometimes make a material that cannot exist in reality, right? So we always need computational and experimental studies to go hand in hand, and so that we can validate our materials that we made in a computer using experiments, and similarly we can help experimentalists to design materials using computational techniques which are much more faster. All right, now here we are. We are in 2022. Our zero energy targets are net zero energy targets by 2050. That's our target. We want to decrease the temperature of Earth by 1.5 degrees Celsius by 2050. But with the pace that we are going in right now, that's not going to happen. With these tools that we have, we are still slow. Even with the computational tools that we have, we are still we cannot reach these targets. So what do we do? What do we need? We need to stop using the coal 5.2 times faster. We need increase of zero emission, decrease in zero emission, zero emission fuels by 12 point something faster, right? So we need these things to happen much more faster pace, and which our experimental and computational techniques are not able to provide us. So we will not be able to reach these targets. So let's talk about the AI part now. So it is, right now, is considered as the fourth paradigm. We started from empirical science to theoretical science to computational science, and now we are talking about data-driven science. Data-driven science has become an important tool for the material discovery. And how that is an important tool, I'll come to that. In my lab, this is just an example, we do two kinds of things. We design material, obviously. We design material for catalysis. By catalysis, I mean producing ammonia, let's say, more sustainably, using new catalysts, new materials. We also try to capture CO2, which is present in the atmosphere. Again, we need new materials. We also try to design materials for fuel cells, for cars, right? And we have been doing this since using experiments and computational techniques. Recently, we have started using AI for this, or machine learning. We are not an AI expert or machine learning experts. We are the users of AI, and we have started using it. And I'm going to show you a quick example of one of the projects that has been done in our lab and how AI helped us. All right, so let's talk about one of the reactions, ammonia synthesis. As I said before, that's a very important reaction where we produce ammonia using nitrogen and hydrogen, and we use a catalyst, iron-based catalyst. But this reaction currently happens at a very high temperature and pressure, and it produces a lot of CO2. It has a 2 gigaton CO2 footprints. We don't need that, and it is a billion-dollar industry. Well, we need a better catalyst. We need a better material to do this reaction, which does not produce CO2 and which does not need fossil fuel energies from fossil fuels, right? So what we have been trying in our lab is to design this material to replace this iron-based catalyst to a new material. How do we do that? So we thought, okay, if we think about all the materials, all the metals that exist in the world, iron and ruthenium have some interesting properties. So I will not go into the chemistry or the details of it, but our strategy was to mix these materials and come up with a new material, new alloy that can actually give us the efficiencies that we need and that could work at lower temperatures and pressures. So, of course, obviously we went to the lab and we tried to design these alloy catalysts. We designed ruthenium and iron individual metals with ruthenium iron alloy catalyst. We did several experiments such as STEM, EDX to see what is the composition, how these materials look like, what is the size of these nanoparticles. So it took us some time. Then obviously we wanted to see the reaction kinetics. We wanted to see what composition works the best. Do I need 20% of ruthenium, 80% of iron, or the opposite, or I need some other composition? What do I need? Then we wanted to see how would this material work at higher pressure? How would this material work at higher temperature? Obviously, we saw better activities at higher temperatures. So we also found a very interesting result here that, well, ruthenium iron is actually poison-free. Iron, after some time, gets poisoned, and it is no more a good catalyst for this reaction. But in this case, our new catalyst was able to do the reaction without getting poisonous. Okay, of course, we want to know, the problem with this catalyst was that the efficiency was not that great. We wanted to know how can we improve the efficiency of this material. So we went with computational tools. We designed this material in a computer. We analyzed several active sites. We analyzed the whole reaction mechanism, how the reaction would happen, how these reaction, different energy states would happen, what are the bottlenecks of this reaction, what is the rate limiting step, and so on. We also could explain why this material cannot get poisoned, in contrast to iron, which has been used since ages. And finally, we were able to explain what we saw experimentally using computational tools. Time period for this project, greater than 1 year. Okay, in the end of 1 year, we had a catalyst that could produce ammonia, which was poison-free, but the efficiencies are not that great, so we cannot commercialize it. We have to keep improving, right? So what's the next step now? We don't have any new technology. We cannot still replace this material. What do we do now? So what are the limitations of this project? Let's go back and see. We synthesized the material, right, in a certain composition using computational techniques. There were several possible ways you can combine these materials to make an alloy system. There are several possible active sites which we didn't even analyze because we could not using the DFT or the state-of-the-art computational techniques. It's impossible. And still it took us more than 1 year to come to this conclusion where we finally said that, okay, this material might not work properly. Okay, well, we have to replace this material. We cannot stop trying. We have to still keep on trying, right? Then that work was done in Japan. I was there. I came to Canada and I started looking into, what materials could be better? What materials exist the most in Canada? We came up with this list. And, we saw this, we can use nickel and copper. Why don't we try nickel and copper? Do I want to spend another 1 year? No. We need the results now. We needed the results yesterday, right? So we took help from AI or machine learning tools. Genetic algorithm to be specific. It's an optimization algorithm where we were able to analyze different compositions of this material, copper nickel. We scanned through thousands of materials, and we were able to come up with a specific composition in a matter of hours. We validated these results with experimental setup very quickly. And also, we are currently analyzing the active sites. Here, there are 96 active sites. If you think about in the previous project that I showed, we only analyzed 9. Right now, we have 96. Imagine the number of years it would take us to analyze all these sites and come up with a right active site for this catalyst. Here, the deep learning and machine learning tools are super helpful for us. And the time that it took is just a few months. So let's come back to our question. Can AI solve climate change? Well, most definitely, as you can see, that we can accelerate our work with AI techniques. Of course, we cannot fully depend on them. We do need our experimental and computational studies. When we come up with few certain materials, we then again have to go back to our computational chemistry tools, experimental tools, go into the lab, make that material, and come back to AI and feed that results in the AI models or the machine learning models. So that's about it. So this is a small snippet of how machine learning or AI can be useful for material scientists for developing new materials for solving the climate change. And thanks to my lab, we are a group of very different people, chemists, physicists, mathematicians who work on these kind of problems. And one thing I would like to say that right now, material science is the field where AI could be very helpful, but it's not fully implemented as compared to other fields. And the reason is there is a lot of lack of data that we need to develop these models, but we're not far. It seems like with the current advances, we can use the current models for developing materials and hopefully expedite the material discovery that we really need for mitigating the climate change. Thank you.
Hi, thank you very much for the presentation. So I'm actually a machine learning scientist who is very worried about climate change, so I decided to start working on material discovery as well.
Perfect, we need you.
Yeah, we should talk. then here's the question and the problem. Coming from machine learning, it depends on data. We need a lot of data, and the field has been releasing data sets to try our algorithms, so and so. And when I started working on this, I was like hitting closed doors because I see that there are data sets and they are protected. You have to pay for them. People don't make them available. It's a completely different thing for me compared to the field. So I would like to hear your thoughts about this. Like given that climate change is, it's highly pressing. We don't have time. I find it like terrible that all the data sets are hidden, proprietary, like people in the field are not releasing their data for others to try, which is alien to some other fields. So yeah, I would like to hear your thoughts about that. Thanks.
That's a roadblock that we need to solve before even implementing AI on material science. We need a lot of data, and that's why there's not a lot of progress in this field. We definitely need to share more data as a scientist, but for many reasons it's not possible. What we are doing, there are two ways. What we are trying to do is we produce, for our initial training, we produce our data using computational algorithms, computational tools. Second thing that we are doing when we are trying to collaborate with synchrotron facilities, like in Canada we have CLS, which is a synchrotron facilities, and there is a lot of data. But of course we had to go through a lot of policy-related issues, and it's still in progress. This is our aspiration that if we are able to collaborate with these synchrotron facilities, which produce a lot of data, and of course if we are able to overcome the barriers of how to share the data, how all the ethical reasons sometimes scientists cannot share data. If we can overcome, definitely there is a solution. But I agree with you 100%. Another ways there are some techniques like Raman spectroscopy, which is really fairly quick and which has not been exploited a lot. So with Raman spectroscopy, you can get a lot of data in few days, for example, for identifying material properties. So we have to be really innovative here because, yes, we have a big challenge that we don't have a lot of data. So, well, here you go. This is the current solutions that we are trying. We are trying to produce certain data artificially. For example, for convolution neural networks, we need a lot of images, TEM images, and it's impossible to get millions of TEM images for a material. A scientist would work for like a decade in order to give us that, right? So we are trying to use computational tools to generate those TEM images, let's say, for example, with defects, which are very important for catalysis field. And we are training the models based on those images. And then, of course, we need testing data, where, again, we go to experimentalists ask for test data. So that's one way. Of course, it's not the perfect way. And there are certain techniques, as I mentioned, Raman spectroscopy, or collaborating with bigger facilities where there are lots of data present, and hopefully, overcoming these barriers. But, yeah, I agree with you. There's no clear-cut answer to this.
Usage of artificial intelligence itself demands a lot of computational power, which demands on energy itself, whether it's contradictory for the aim of resolving the problem of climate change.
Absolutely. You are absolutely right. This is a question of, we definitely need to make a comparison. We use supercomputers that need a lot of energy to run. Even for these computational analysis, computational tools like density functional theory, even for doing, let's say, just to give you an example, for like 40 atoms, sometimes we take 2 days, the computer is running nonstop. And it generates a lot of heat, it takes a lot of electricity. Are we doing a just test there? If we say that, okay, we need AI. So that's definitely a question of, a question where we should compare the energy that we are putting in to do what we are getting out of it by doing all these, implementing new techniques. That's definitely a very good question, and I don't have the answer. We need to compare, but if we think about the current state of the art, we don't, just based on the material science, and this is a very narrow subject that I'm talking about, can we just solve our problems of innovation, of, for example, improving the material efficiencies? Fuel cell cars are there since a long time. This technology exists there, but we are not using that. It's not worldwide. It can only help the climate change if everybody in all the countries can use those fuel cell cars, but we are not able to use it because the materials are very expensive. We cannot afford them. It's not efficient, and so on. So with the current state of the art, can we come up with a better solution in the time frame that we have, the limited time frame we have? So I agree with your question. It's difficult to say at the moment what would happen, considering that these computers need a lot of energy. But at the same time, we need to try whatever tools we have on our hand and hopefully innovate things. And we cannot just say that we make fuel cell inventions and we can solve all the problems. We have a spectrum of technologies that we need to work and improve on in order to mitigate the climate change. So valid question. Again, very difficult question for me to answer, as there is definitely a strong comparison that needs to be done in order to answer that.
Yeah, in such a case, I just wanted to a little bit add up. So you focused on improvement of catalytic materials, but maybe the answer to this question, if it's really such a strong comparison, such a difficult comparison, whether or not it's necessary to spend a lot of resources on it, maybe the question should be found in different branches of science. For example, chemistry, which can propose different way of working without using this particular reaction. That was like my point.
Absolutely, we might not. Use the traditional ways and may be able to get the answer that we are looking for, develop more technologies. Well, based on just the computational analysis that we do, sometimes the computational tools that we use, we are running computer even more than when we use AI techniques. So those computational analyses were done over years, and we use supercomputers throughout that year. And that probably generated a lot more heat and needed a lot more energy than using these genetic algorithm-based techniques, which could be done on a workstation. So while it definitely depends on the techniques you're using, and I agree with you, we cannot completely depend on AI. We might find solution using chemistry techniques or the basic principles of physics. The answer, the problem is we don't know where the answer lies. So we are trying to expedite our discoveries by using AI. And specifically in those cases where we are already putting a lot of energy in these supercomputers. So can we cut down that time? And that's where I think AI could be very helpful to reduce the supercomputational resources that we are using.
Thank you. We have another question here.
Of course.
Yes, thank you very much. Very beautiful presentation, and the graphics and the elephant and the dragons.
Right.
I will talk about it with my kids if we still have a planet,
Yes.
So you said you used the IPCC State of Climate Action 2021 report, saying we need 13 times faster ramp up public and private climate finance. You're a scientific, so you have a goal, you do it. And I know some scientists in UK, they like part of a rebellion, they chain themselves. So for example, I think cars, even electric car, is already too much, we should not work, and we should just work on doing like a neighborhood that you don't need car, you don't even need a bus, you just go with your bike, you walk, So are you part of a movement and you say, no, we don't work on this, we're going to work on that. So how do you leave that on the
I definitely believe in that, because if you think about how much energy we are putting in these cars, electric cars, actually, where is electricity coming from? right? It's not fully coming from renewable sources. We still burn fossil fuels. So are they green? You know, it's difficult. It's a very challenging. So we cannot say that the technology is there yet. We are working towards it. It's not. Even fuel cell industry, if we are able to develop a catalyst that is cheaper, that can make the car less expensive, everybody can afford it, but still we are putting hydrogen in it. We need another technology where we can produce hydrogen renewably. So there are various aspects of these new innovations, new technologies that are coming up as a potential green technologies, but we are not there yet. And I agree with that. It's sometimes it's better to plant more trees in some cases and get rid of CO2. So should be a very well thought, and I'm a chemist, I'm a material scientist, but for policymakers, for economists, I think it's a very good question that where should we go from here, whether these technologies are helping the climate by we are putting so much energy, money, resources into developing these new technologies, or whether we should simply find solution for deforestations. So I completely agree. And I personally believe that we need a portfolio of solutions. One solution is not enough. So I belong to material scientist community, and that's what I have taken the role of, and I try my best to innovate materials, but it needs a collaborative effort if we want to mitigate the climate change. So definitely I agree with you on that.
Thank you. We have another question here.
Hello, thank you for the presentation. And since we know that climate change and battling climate change is a collaborative effort, do you think with the rise in the number of impact funds, the bottleneck caused by expense can be solved and the climate change goals can be achieved faster, or do we need more effort from their side as well to increase the funding available?
Sorry, can you repeat that question? I'm sorry, I couldn't hear it.
So with the rise in number of impact funds that are helping battle climate change, do you think they should start doing more and they should provide more funds to scientists or
well, that would definitely help. I'm a scientist, so yes, I would say yes. We need more passion, we need to recruit more students, more HQPs, more great minds to focus on these technologies, to develop these technologies. And it has to be multidisciplinary effort. It's not just chemistry, material science, or mathematics or AI. It has to be multidisciplinary efforts. We need, but as a scientist, I would say yes.
Thank you. We have time for one more questions, if so. Okay, if not, let's thank our speaker.
Thank you so much.